Okay, March 2022, paper 4, variant 2. Question 1. A ball rolls down a ramp onto a horizontal surface. The first section of the horizontal surface is smooth, and the second section of the horizontal surface is rough. Okay. Figure 1.1 shows the speed time graph of this ball. State the time when the ball reaches the start of the rough section. It was going down a slope and then onto a smooth surface, then to a rough section. What happens in a rough section? That's the question. What happens to the speed of the ball in the rough section? Starts to decrease. Why? Due to friction. When did it start to decrease? When did the speed of the ball start to decrease? At this point, right? At this point exactly. Yes. What is the time that corresponds to this point? Let's check out the time. Okay, if you draw a vertical line, yes, if you draw the vertical line, it would be at, yes, 2.2, exactly, 2.2, not 2.4, not 2 point anything, it is 2.2 seconds, 2.2 seconds. Explain how figure 1.1 shows that there is no resultant force on the ball when it's rolling on the smooth surface. When it's moving on the smooth surface. No resultant force. What does no resultant force mean? Again, let's recall, what does no resultant force mean? No resultant force means constant speed. Constant speed. Yeah, from the graph, we can say that it is moving with a constant speed. Okay? Constant speed. And from the graph, I can see that it's moving with a horizontal line, right? A horizontal, okay, or you can say that the gradient or the slope, okay, is 0. The slope is 0. Using figure 1.1, determine the acceleration of the ball as it rolls down the ramp. Can I find the acceleration of the ball? Yes, I can find the acceleration. I need to calculate the slope, right? You need to find the slope, which is y2 minus y1 over x2 minus x1. So from the graph, I need to take 2 points. This is the first point, y2 minus y1. Can I take the second point to be 0 and 0? Yes. You can take the second point to be 0 and 0 because they are both on the same straight line. So the first point, this would be 12.8 and 1.5, right? 12.8 divided by 1.5. What would this be? 12.8 divided by 1.5, which is 8.5 meters per second squared. Okay, can I say 12.8 minus 0 over 1.5 minus 0? Yes, which is 8.5 meters per second squared. The ball starts from rest at the top of the ramp. Show that the length of the ramp is 9.6 meters. Distance. Can I show that the length of the ramp is 9.6 meters? Yes. Distance is the area under the graph. So the area, which is a triangle, half times base times height. The base is 1.5. The height is 12.8. So what's half times base? 1.5 times height 12.8 times 12.8. So this would give you exactly 9.6 meters. 9.6 meters. Okay, quite simple. Okay, one of the very common questions in paper 4. Figure 2.1 shows a spring balance used to measure the weight of the baby. The spring inside the balance extends when a mass is suspended from it. The dial shows the extension of the spring as the value, okay, as a value of mass in kilograms. The spring obeys Hooke's law. State Hooke's law. What is Hooke's law? Hooke's law is when you say that the extension and the force and extension are directly proportional unless reaching the limit of elasticity or the limit of proportionality. Okay, force and extension, okay, are directly proportional unless reaching the limits, okay, of elasticity or the limit of proportionality. You can say so. State the relationship between the mass of the baby and the force exerted on the spring due to the baby. What is the relationship between the mass and the force? Aren't they both? Aren't they? Or how can I relate? How can you relate the force? What is the force of the baby? The force of the baby is the weight, isn't it? Right? The force of the baby is the weight. So it is directly proportional to the mass, which is weight equals mg. Weight, okay, or force is directly proportional, okay, directly proportional to the mass due to the equation which is weight equals mg. The reading on the spring is 8 kilograms. Determine the force exerted on the spring due to the baby. Okay, weight basically weight equals mg. Hmm. Let's use the new g, which is 9.8. 8 times 9.8. What's 8 times 9.8? This is 78.4. So the force is 78.4 newtons. Okay. The limit of proportionality for the spring is okay, of a force 175 newtons. So this is the limit. This is the limit. Sketch the extension load graph for the spring. The sketch must continue beyond the force of 175 newtons. So before 175 newtons, until it reaches 175 newtons, it is obeying Hooke's law. It is directly proportional, right? It is directly proportional. So you will draw a straight line, a directly proportional line, a straight line from zero, okay? And it will reach any point at 175. Do I have to reach some certain extension? No, he did not state the exact extension. So it will extend. You will extend the line to one of these points, whatever. And then beyond the 175, what happens is that it's no longer directly proportional, right? It's no longer directly proportional. So it will curve upwards or downwards towards which axis? Towards the extension axis, right? Always towards the extension axis. It's not a must that it has to bend towards the y-axis. No, it's a must that it will bend towards the extension axis. Why? Because you don't need that much load. You don't need that much force to extend the spring. It's broken. It is broken. It's no longer obeying Hooke's law. The baby is carried out from the ground floor to the bedroom. The vertical height of the bedroom above the ground is 3.5 meters. Calculate the gravitational potential energy, the change in gravitational potential energy when the baby is carried from the ground to the bedroom. Gravitational potential energy GPE equals mgh, right? GPE equals mgh. You have the mass 8 and basically GPE equals mgh. So 8 times 9.8 times the height, which is 3.5 times 3.5. This is 274.4. 274 joules. 274, okay, joules. Now, question 3. Describe the process by which the volume of the water in the puddle decreases. How does the volume of the water decrease? Volume of the water decreases due to evaporation, right? Evaporation in which the most energetic molecules escape from the surface, right? Evaporation, okay, most energetic molecules, okay, molecules escape from the surface. State and explain one change in the weather that would cause the volume of the water in the puddle to decrease more slowly. More slowly. We need to decrease this rate of evaporation. How can you decrease the rate of evaporation? How can I decrease the rate of evaporation? Change to the weather. So you need a colder temperature, right? You need a colder weather. Okay, why? Because you'll have less energetic molecules that will escape, so you'll decrease the rate of evaporation. Okay. Colder weather, colder weather, what will happen? Colder weather, you'll have less molecules will have enough energy to escape. Okay, energy to escape. You can also say that the rate of evaporation decreases. Explain in terms of molecules how sweating helps to cool your body on a hot day. How does the sweating help to cool your body? Basically, again, due to evaporation. You need to say that the sweat water molecules escape from the surface, right? Leaving behind the least energetic molecules, right? Leaving behind the least energetic molecules, causing a cooling effect or decreasing the average temperature. Most energetic molecules, okay, escape from the surface, leaving behind, leaving behind the least energetic molecules, decreasing the average temperature, okay, decreasing the average temperature of the body. Hmm. Okay, a sample of mass has a volume of 0.05 meters cubed, the density, specific heat capacity. Okay, can I find the mass of the sand? Yes, I can find the mass of the sand. You have the density and you have the volume, right? So mass equals density times volume. 1900 times volume 0.05. What's 1900 times 0.05? This is 95 kilograms. Calculate the thermal capacity. This is cancelled. You're not required to solve for thermal capacity. The initial temperature of the sand is 7 degrees Celsius. The sample of sand is heated using an electrical heater. The power of the element is 50 watts. Calculate the time taken to increase the temperature to 19 degrees Celsius. So can I find the time taken? Yes, I can find the time taken. You have the mass, you have the energy. Okay, do you have the energy? Yes, you can find the energy, or you have the power. I'm sorry, you do have the power. So basically, we say power. Oh, sorry, we don't have the specific heat capacity, do we? No, we do have the specific heat capacity. We do have the specific heat capacity, which is 1,500. So basically, power times time equals mc delta t. You need the time, so you'd say time equals mc delta t over power. Mass is 95 kilograms. The C is 1,500, right? 1,500. Delta T, the change in temperature, it was 7 degrees, became 19 degrees. So 19 minus 7, 12 over the power, which is 50 watts. And you do not need to convert the power. 95 times 1,500 times 12 divided by 50. 34,200 seconds, right? 34,200 seconds. So it's a lot of time, yes. If you want to convert it to minutes, if you want to convert it to hours, as you like, or you can just leave it as it is. 200 seconds. In some countries, the soil is too cold for the plants to grow well. In these countries, the plants are grown in plastic pots and kept inside. The pots contain soil and are placed on sand. The sand is heated using this electrical heater. Describe in terms of molecules how the thermal energy is transferred from the heated sand through the base of the pot. Through the base of the pot. This is how can you transfer this energy? Due to basically by conduction, right? By conduction, in which the molecules gain kinetic energy, right? By conduction, molecules gain kinetic energy and they vibrate more and they transfer energy. Okay, transfer energy to neighboring molecules, to the neighboring molecules by lattice vibration. Okay, by lattice vibration. The heating element in figure 4.1 remains switched on. The temperature of the sand remains constant at a value above room temperature. Explain why the temperature of the sand remains constant. Why does it remain constant? Think about it. Okay, you keep on heating the sand. The heater is switched on constantly, but for some reason, the temperature of this sand remains constant. It does not increase. Why doesn't it increase? We'll say because there's energy lost. Yes, energy is lost to the surroundings. Okay, the energy is lost to the surroundings at a rate which is equal to the energy gained by the sand. So you can say it loses 10 joules per second, for example, which is a lot maybe, 10 joules per minute, and it gains 10 joules per minute. So the same amount, okay? It loses the same amount it gains. So energy is lost to the surroundings, okay, as heat, which is equal or at the same rate, you can say at the same rate, at the same rate it is gained. Hmm. Okay, boy looks at the image of a clock in a plane mirror. Figure 5.1 shows the mirror, the clock, and the position of one of the boy's eyes. On figure 5.1, draw a ray of light from the clock reflected to the boy's eyes. To the boy's eye. On figure 5.1, mark with an X the position of the image of the clock. State whether the image formed by the mirror is virtual or real. Anyway, can I draw a ray from the clock to the boy's eye? Yes, I can do that. Basically, a ray to the mirror. I need to, as much as possible, draw a ray to the center, to a point which is almost at the center, between at the distance between the clock and the boy's eye. So, for example, at this point, this might be the center from the clock to the boy's eye, and then you need to draw a straight line from the mirror, okay, and definitely this line is using your ruler, okay, using your ruler from the clock to the mirror, and then at this point you need to draw a normal line and make sure that the angle of incidence is equal to the angle of reflection. Angle of incidence has to be equal to the angle of reflection. So this is the first point. You drew a line from from the clock to the boy's eye. Okay, not bad, right? Second point is that we need to draw the position of the clock, the image of the clock. Can I draw the position of the clock? Yes, I can draw the position of the clock. How can I do that? You can measure the distance from the clock to the mirror and then measure the same distance from the mirror to the clock, and this is the mark with the point X, okay, the position of the clock, okay. Make sure that they are the same distance. State whether the image formed is virtual or real. Hmm. Any image formed in the mirror has to be a virtual image, right? Why is it a virtual image? Any description of a virtual image is that this image cannot be produced on a screen, okay, cannot be produced on a screen. Figure 5.2 shows the image of the clock seen by the boy. The boy now looks directly at the clock. This is the image, right, of the clock seen by the boy. He's seeing this image. On figure 5.3, draw what the boy actually sees when he looks directly at the clock without looking at the image of the clock. Hmm. Can I see the actual image? Yes, I will see the actual clock, which will look, it will have this one pointing upwards, but the other one will be pointing to the left. It's laterally inverted, not, it is not vertically inverted. It is not vertically inverted. So if something is pointing upwards, it will keep on pointing upwards. If something is pointing downwards, it will keep on pointing downwards. But what's pointing left will point to the right and vice versa. That is what we call laterally inverted. Okay? What is the meaning of a monochromatic light? Monochromatic means one frequency. One frequency. Light has a wavelength of 5.6. Can I find the frequency? Yes, frequency equals speed over wavelength. 3 times 10 to the power of 8 over wavelength, which is 5.6 times 10 to the negative 7. Okay, 5 times 10 to the negative 7. Can I find the frequency? Yes. Okay, 5.6 times 10 to the negative 7, which is 5.35 or 5.4 times 10 to the power of 14. Okay, 5.4 times 10 to the power of 14 hertz. Okay, figure 6.1 shows two bar magnets. Sketch the pattern and direction of the magnetic field lines between the two bar magnets. Can I draw the field lines? Yes, from north to south. Okay, from north to south. Okay, figure 6.2 shows the same bar magnets. Name the parts labeled A. What are A? What, what is A? What is A? Can you say that this is a split ring commutator? Is this a split ring commutator? No, it's not. Why isn't it a split ring commutator? Because this is a generator. How do I know that this is a generator? Because you have a galvanometer. You have a galvanometer. So basically, you are rotating this wire. Okay? You are rotating this wire. So this is a generator. So these are not this is not a split ring commutator. This is a slip ring. Okay? Slip rings. Okay, coil of wire is rotated. On figure 6.2, draw an arrow to show the direction of the current in the coil. Explain your answer. Can I show the direction of the current in the coil? Yes, I can show the direction of the coil. Using what? Using Fleming's left or right? Think about it. Left or right? This is a generator, so I'm using Fleming's right hand rule, right? Fleming's right hand rule. First finger, the index finger, it's from the north to the south, right? Pointing to the right. And then the second finger, the middle finger, this is the direction of the current. I do not know the direction of the current yet, but I do know the direction of the force, right? I do know the direction of the force. So the direction of the force on the left hand part is upwards. Why? Because the direction of the rotation is in this way, right? And the direction of the force on the right hand part is downwards. So my thumb should be pointing upwards on the left hand part of this coil. Therefore, the current in this part would be pointing inwards. This would be the current. It would go inwards and then come outwards from the other part. This is the direction of the rotation of the current in the coil, right? Okay, this is a this is how it will go. How can I explain? Basically, if you want to explain, you can say that the force on the wire the magnetic field, okay, force on the wire, the magnetic field and the current are all perpendicular to each other, okay, to each other. You can also say due to Fleming's right hand rule. Due to Fleming's right hand rule. Explain how rotating the coil continuously causes the galvanometer needle to show an alternating current. How does the galvanometer needle keep on showing an alternating current? How does it keep on uh, moving or deflecting left and right? It keeps on deflecting left and right. It's not that hard. If you think about it, continuously, the coil keeps on moving continuously, keeps on moving up and down. As it moves up, what happens? It cuts. You have to talk about cutting. It cuts the magnetic field, inducing a current in one direction, right? Inducing an EMF and a current in one direction. And then, as it moves, as it cuts in the opposite direction, the magnetic field or the current will be induced in the opposite direction. So, as the coil cuts, okay, the magnetic field, okay, as it cuts the magnetic field, an alternating current, a current, okay, and induced, okay, an induced EMF is created or generated in the coil, okay. EMF is generated in the coil, and induced EMF is generated in the coil, okay, and the current is produced, and a current moves in the coil, for example, in the coil. So now this is if it's moving in one direction. As it moves, okay, as the coil cuts in the opposite direction, okay, as the coil cuts in the opposite direction, the current, okay, the current is generated or moves in the opposite direction or is reversed. Hmm. Okay, so far so good. The 12-volt battery consists of cells connected in series. Each cell has an electromotive force of 1.5 volts. Can I find the number of cells? Yes, 12 divided by 1.5. What is 12 divided by 1.5? It is 8 cells. So you have 8 cells in series, right? When the switch is closed, the ammeter reading is 2.4 amperes. Calculate the total resistance of the circuit. Can I find the total resistance of the... Okay, you have the total voltage and you have the total current. R equals V over I, right? R equals 12 over 2.4. R equals V over I, 12 over 2.4, which is 5 ohms. This is the total resistance of the circuit. Each lamp has a resistance of 3 ohms. Calculate the resistance of Q. Each lamp has a resistance of 3 ohms. Can I find the resistance of Q? Yes, these two lamps together, they are in parallel. So the total resistance of these two lamps is what? Is 1.5. How did I know that? It's a rule of thumb. I told you before that if you have two resistors or two lamps which are equal in resistance, and they are parallel, they are equal in resistance, then the combined resistance would always be half, right? It would always be half one of them. If you want to make sure, product over sum, right? So product over sum, 3 times 3 over 3 plus 3, right? 9 over 6 is 1.5 ohms. These are the two lamps These are the two lamps. Can I find Q? Yes. The total resistance of the circuit is 5 ohms minus the two lamps together, which is 1.5, which gives you a resistance of 3.5 ohms. Okay, a total resistance of 3.5 ohms. Again, total resistance of the circuit is 5 ohms. Both lamps together 1.5. Okay, 1.5. So 5 minus 1.5 is what is 3.5 ohms. On figure 7.1, draw the symbol for a voltmeter that measures the potential difference across the two lamps. Can I find, can I draw a voltmeter? Yes, I can draw a voltmeter across the two lamps. Okay, across the two lamps this way, a voltmeter across the two lamps. Piece of cake. Calculate the power supplied to one lamp. Can I find the power supplied to one lamp? Yes, I can find the power supplied to one. How can I do that? Power equals IV, right? Power equals IV. Okay, what is the voltage? What is the voltage of each lamp? How should I know? How should I know the voltage of each lamp? You don't have the voltage of each lamp. You do not have the voltage of each lamp. Can I find the voltage? Yes, you can find the voltage of each lamp because you have the resistance and you have the current in each lamp. Do I have the current in each lamp? Yes, you do. You have the total current in the circuit, which is 2.4 amperes, right? Have total current in the circuit, which is 2.4 amperes. So 2.4 amperes. And then at this junction, what happens to 2.4 amperes? It gets split, right? It gets split because they are equal. So this lamp will get 1.2 amperes and the other lamp will get 1.2 amperes, right? Right? Because they are equal. So they're equal. The current gets equally split between the two lamps. You have a current and you have a resistance. The resistance of each lamp is what? Resistance of each lamp is 3 ohms. Not 1.5. The resistance of each, we're talking about one lamp. So the resistance of one lamp is 3 ohms. Can I find the voltage of one lamp? Yes, voltage of one lamp. V equals IR. Right? V equals IR, so 1.2 times 3, which is 3.6 volts. Now, power equals IV or VI. 1.6 times 1.2 times 3.6. What's 1.2 times 3.6? This is 4.32 or 4.3 watts. Okay? Can I use another equation to find the power? Yes, you can use another equation to find the power. Power equals I squared R. You have the current, I squared, 1.2 squared, times the resistance, times 3, it would give you 4.3 watts. You can use this equation, yes. A radio is connected to the main supply using a step-down transformer. Draw a labeled diagram of the structure of a basic step-down transformer. Okay, that's not too hard. You have the core, iron core. Okay, you have to state that this is an iron core. And then step-down transformer, you have more coils on the primary, and then you have much less coils on the secondary, right? This is the primary coil made out of copper, okay? Primary coil which is made out of copper. And this is the secondary coil, which is made out of also copper. You have the primary and you have the secondary coil, which are both made out of copper. Explain the operation of a basic transformer. What is the operation of a basic transformer? Simply, you have an alternating current in the primary coil. Okay, an alternating current in the primary coil. What does it do? Creates or generates, okay, an alternating, okay, an alternating magnetic field, okay, which cuts the secondary coil, inducing, yeah, inducing an alternating EMF and current, EMF and current in the secondary coil. Okay, voltage in the main supply is 230 volts. The output voltage is 6 volts. Input primary 230, output secondary 6 volts. Can I find the ratio? I'm not asking about specific number. I'm not asking about the primary number of coils or number of turns in the primary or the number of turns in the secondary. I want to find the ratio NS over MP. So if I want NS over MP, NS over MP, this would be equal to VS over VP, right? The output over the input, the secondary over the primary, 6 over 230. What is 6 divided by 230? This is 0.026. Should I just leave it as it is? Yes, 0.026. It has no unit. It's a ratio. Okay. Question 9 is cancelled, definitely. Yes, it has been removed. Question 10. The isotope americium 241 is represented by, it produces neptunium and an alpha particle. So alpha particle would be 4 and 2. Can I find the neptunium? Yes. 95. So this would be 93 because 2 plus 93 is 95. And this one would be 237 because 4 plus 237 is 241. Okay. Describe how the americium ionizes air. Basically, how does the americium ionize the air? Due to the alpha particles, right? Produces alpha particles as it decays. It produces these alpha particles. These alpha particles, what do they do? What do they do? Yes. How do they? Yeah, they remove electrons. صح? They're positively charged, so they remove electrons from the air molecules. So as the alpha particles move close to the air molecules, they remove electrons from them. Okay, okay. As alpha particles move close to the air particles, they remove remove electrons from them. Suggest and explain two reasons why the smoke detectors use an isotope that emits alpha particles rather than an isotope that emits gamma radiation. Definitely, gamma radiation is too dangerous, right? Gamma is too dangerous, so we'd say that alpha is less harmful to human beings. Also, alpha is less dangerous to humans. You can also say that the alpha is less penetrating, or that the range traveled in air, okay, the distance traveled by in air by alpha is much less. Okay, the distance traveled in air by alpha is much less. Hmm. Okay. Okay.